We're going to section 3.1, unit 3. Unit 3 is based almost exclusively on the parabola. That's why I had you practice the parabola really quick, and I would suggest that you practice it some more. So the first thing we're going to talk about, again, this first section, whereas the other 3 sections of this unit are not primarily review, the first section is kind of a review of what we go over in intermediate algebra with a little bit of an extension at the end. We're going to talk about these things called complex numbers. So again, if you know this, you are right where I need you to be. Hopefully you're bored and exhausted by most of this section. But in case you're not, there's no problem. You can learn it right now. So complex numbers, where these things originated in math history is from this graph of the parabola. Notice this graph right here is the parabola that we just did the basic graph of, but it's been shifted up 1 unit. Okay, so it's up 1 unit right here. So the equation is f of x is equal to x squared plus 1. And at some point in history, because math people are sometimes kind of crazy, somebody said, what would the solution to this equation be? X squared plus 1 equal to 0. So when we bring the 1 over to the other side, we say that that's the same thing as x squared is -1. And we've been told our whole lives, and you've been told your whole arithmetic life, that you can't square something, get a negative. You can't take the square root of a negative number. And as far as the real number system is concerned, you are totally and completely right. But some crazy mathematician trying to make our lives more complicated said, what if I made something up? And so made something up called the imaginary unit. Okay, I'm sure you've heard all about this before. The imaginary unit is going to be the number that solves this equation. And so we start a whole new branch of mathematics. If you are going on into more math and you ever get the chance to take complex algebra, it's fabulous. It's glorious, fun times in algebra. Again, some of you never want to take math after this class again, and I respect that as well. So here's the imaginary unit. Imaginary unit is the value that solves this. And so the imaginary unit is defined. This is the definition. This is what we have to know. The definition of the imaginary unit is that I is equal to the square root of -1. Okay, this is given to us. We don't make this up. This is made up for us. Okay, so I'm just going to write over here, this is the definition of the imaginary unit. And so we are going to spend a little bit of time here in our section 3.1 getting to know how to use the imaginary unit. Now, there's a corollary to this definition. I don't know that I can spell corollary, but this isn't spelling class, so that's okay. The corollary is that if I square both sides of this, I get I squared is equal to -1. So this is information to know. This is super important for your future in this class. Okay. If any of you are planning on being any sort of electrical or computer engineer, even a programmer, the imaginary unit comes up in a lot of fascinating different ways in real world applications. So it becomes super important. All right, so from that, then we get this definition, complex numbers. We're now creating a bigger set of numbers than the real numbers, that if A and B are any real number, then A plus BI is called a complex number. The A term right here, this is the real part of the complex number. And then the BI, that is the imaginary part. So I've just made a bigger set of numbers. All real numbers are complex numbers with no imaginary part. So if I cover up the imaginary part and I just consider the real parts, well, yes, those are the real numbers, but they are also part of the complex numbers. And then if I cover up the real part, these things that we would call imaginary numbers, our book calls them pure imaginary numbers. I'm not super concerned about the terminology on my test, but just in case you encounter it on the homework, the pure imaginary numbers are also complex numbers. And so then together as well. So we're first going to get used to working with our imaginary unit and then working with complex numbers. So first things first. Example 1, I want to simplify the square root of -16. Okay, I want to write this as an imaginary number. Okay, so this is, if you remember simplifying square roots, which we're going to review a little bit here, this is no different than any square root you've ever simplified before. What we're going to do is we're going to break this apart into things we can take the square root of. And so whenever you see a negative under your radical, you are going to say that that is -1 times something. And in this case, can I take the square root of 16? That number, is that a perfect square? Yes, sure. Okay, so I'm just going to write 16. And now I can take the square root of the parts by the product rule of radicals. Again, you don't need to know the terminology. Product rule of radicals just says you can take the square root of the individual parts underneath your square root. So what's the square root of -1? What's that defined to be? I, yes, thank you for those of you that are still awake this morning. And then what's the square root of 16? 4. And so 4i, that is my imaginary number. Okay, even though we can take the square root of negative numbers, we don't like the negatives to be there, so we will always write them as some form of I. All right, exercise 1, exact same thing, just a different number so that you get the thrill of writing it down. Okay, so once again, this is just an exercise in simplifying radicals. If you've never seen simplifying radicals before, see me after class. I've got some videos from my intermediate algebra class I can share with you to get you up to speed on this. So square root of -81, I'm going to break this apart into the square root of -1 and then times 81. 81 is a perfect square, so that's good. And so now the square root of the -1, humor me, what's the square root of -1? I, yes, that is the whole big thing from this section. And then the square root of 81 is 9. Beautiful, 9i. That's my imaginary number. Excellent. The next example is the same sort of thing, but this time I have a number that's not a perfect square. This is my effort to remind you about simplifying radicals. So again, we're going to write this as an imaginary number. So the negative I'm going to write as -1, but then I've got this 75 to contend with. Now remember, in general, in case you don't remember, we did talk about this when we talked about the distance formula on our first day together. When I simplify a radical, my goal is to find a number that divides into this. That's a perfect square. What's the number that's a perfect square? Does anybody recognize? Yeah, so you just go down the list of perfect squares. 2 squared is 4. That would be the first number to start with. Use your calculator. 4 doesn't go into 75. Okay, 3 squared is 9. 9 is a perfect square. 9 doesn't go into this. 4 squared is 16. 16 doesn't divide into this. Then you get to 5 squared. 5 squared is 25, and it goes in. And your calculator will tell you that this is 25 times 3. Again, if you don't remember how to simplify radicals, this is something that is going to be part of this unit. I don't have time to do a full reflection on it, but I do have resources that I can share with you. So the square root of -1, one more time. I, yes. When I write this with a radical, I'm going to show you how I write it. I'll give you the reason why. The square root of 25 is what? 5. Now that I've taken the square root of 25, I do not need the radical over that anymore. So I'm going to write that as a 5 in front of my I. And then the square root of 3, since the square root of 3 is an irrational number and I don't want to approximate, I'm just going to leave it as square root of 3. Because I write very messy, you could write this as 5 square root of 3 times I, but our book doesn't tend to do that either, simply because we don't want you to think that the I is under the radical, because someday if you take enough math, the square root of I becomes another really fun thing, and that would be bad notation. So that we don't want the I under the square root. Yes? Just be clear that the radical is not going over the I, and I'm totally good with it. Yes. All right, so exercise 2, same thing, just a different number, giving you a chance to simplify the square root of -24. So the square root of negative 24, I'm going to first start off with that -1. And then what is the perfect square factor of 24 that I'm going to use? 4, yes. If anyone in here broke it up into 8 times 3, I would completely agree with you that 8 times 3 is 24, but that doesn't help you because neither 8 nor 3 is a perfect square. So it doesn't help me simplify this at all. So you always want to pick a number that's on your perfect square list. All right, so the square root of -1, again, that's I. I've asked you that 4 times now, so hopefully you're realizing what that is. The square root of 4 is 2. Since I've taken the square root, it comes out of the radical. And then the square root of 6, since that's an irrational number, I'm not approximating. I'm going to leave that under the radical. You with me so far? We're doing okay. Okay, this isn't going to go away. We're going to keep doing it, but now we're just going to transform into a slightly different problem here. So now we're going to multiply these two numbers that have negatives under the radical. And I know that if you're like me, when I first learned this 50 years ago, you want to just say, oh, okay, -5 times -10 is 50. So this is the square root of 50. But complex numbers, imaginary numbers, they function a little differently. So before I can do that, what you have to do first is you have to convert each of these to its imaginary unit. So what I'm going to do first is I'm going to say, okay, the square root of -5 is going to be I square root of 5. Does everyone understand where that I came from? There's a negative under there, so that's a -1. So I'm just pulling that out as the I. All right, and then what would the square root of -10 be then? I square root of 10. Fantastic. Well said. Now I'm ready to go ahead and multiply them together. So before you do any operations, you have to write these in imaginary notation. And now when I multiply the stuff outside the radical, the I times the I, yeah, it's going to be I squared. Just like X times X is X squared, Y times Y is Y squared, I times I is I squared. And then the square root of 5, square root of 10 is square root of 50. Now I'm ready to simplify. We're just about done with the problem. Does 50 have a perfect square factor? Can I simplify that at all? 25, yes, I'm trying to keep the numbers nice and reasonable. So I've got I squared, and then 50 is 25 times 2. And now here's my one more question. If you look up at the definition of the imaginary unit, you can answer this question. What is I squared equal to? -1. Yes. Okay, so that's -1. I'm just going to write a negative because we're going to multiply by, what's the square root of 25? 5. So I got -5 now, and then square root of 2. So because I squared is -1, that's where this negative outside the radical comes from. All right, exercise 3. You get your own chance to do the same exact thing, although I've made the numbers perfect squares in this first one, just to practice the I stuff. So both of these numbers in this one are perfect squares. So I can do this in kind of one step. What's the square root of -9 going to be when I take the square root of that? Okay, the square root of 9 is 3, and then the square root of the negative is I. Great. So even if you did that in 2 steps, at some point you have 3i. What's the square root of -25? What does that simplify to be? Okay, 5 is the square root of 25, and then times I. You need both. You need the 3 in the I, and you need the 5 in the I. Now we're ready to go ahead and multiply. 3 times 5 is 15. I times I is I squared. And if I have 15i squared, since I squared is -1, this becomes what? -15. Excellent. Well done. I appreciate that. Exercise 4 is very similar to my example where you've got numbers that right at the face of it are not perfect squares. So you're going to have to multiply and then simplify. Okay, so the first one, the square root of -6. What can I do to simplify the square root of -6? How about that negative under the radical? How does that simplify? There you go, thank you. I square root of 6, square root of -15 becomes what? I square root of 15. So the difference between this and the previous example that you did is in this one, the 9, I could take the square root of and get 3. Here, the 6, I can't take the square root of at this point. That's why it might look a little different to you. Now I'm going to multiply. So the I times the I gives me I squared. The square root of 6 times the square root of 15. 6 times 15 is square root of 90. Well, 90 has a perfect square factor. What's the perfect square factor of 90? 9, perfect. It's staring us right in the face. It's 9 times 10. And now I'm ready to simplify this and finish. What's the square root of 9? The square root of 9 is 3. The I squared makes that what? -3, yes. And then I've got square root of 10. And there's my simplifying. So that's just beginning to learn how to work with our imaginary numbers. I'm going to flip to the back page of the sheet. Now that we have a little bit of experience working with imaginary numbers, we're going to go through the 4 basic operations with complex numbers. And actually, 3 of the 4 operations, even if you've never seen complex numbers before, you should know how to do. They're just introductory algebra concepts. So the first one, example 4, I am asked to add, notice the plus sign, that is important. I'm asked to add 2 complex numbers. Well, if before class I did not tell you that I was the imaginary unit, if I was just a variable, what would you tell me to do to these 2 things? To collect what? Like terms. Yes, that's all adding complex numbers is collecting like terms. You add the real parts with other real parts. You add the imaginary parts with other imaginary parts. So here goes. 4 plus -6. When I add the real parts, I get -2. And then 3 plus 8. When I add the imaginary parts, I get 11i. And remember, when we add like terms, we don't do anything to the letter. The letter just stays what it is. We're counting. So please do exercise 5. I would like you to add those 2 complex numbers, please. Okay, so when I add the real parts, 9 plus 8 gives me, yes, thank you for being awake. And then -4 plus 7 gives me how many i's? +3i, great. That's adding complex numbers. It's just adding like terms. And the same thing kind of goes for subtracting. But if you had had me way back in introductory algebra or whenever we started talking about collecting like terms, and if we saw something like this, I would have given you a suggestion so that you don't make a little kind of silly mistake. This negative, this subtraction sign, that subtraction sign applies to everything that comes behind it, not just the first term. Okay, common mistake is students will be good at subtracting the 13, but then completely forget about subtracting the -5. So what I encourage you to do, until you get used to that, is I would distribute the subtraction sign. Treat it like a negative. That way you're going to avoid making a little blunder that is going to cost you points when I know you know how to do this. Okay, so I'm going to do that. So I've got -2 minus 11i, and now I'm going to distribute the negative. So a negative times the positive 13 is -13, and a negative times the negative 5i is plus 5i. Now I'm ready to collect the like terms, just like we did on the previous problems. My real parts are the -2 and the -13, so that becomes -15. The imaginary parts are -11i plus 5i, and that is -6i. So distribute, then collect your like terms. And do that on exercise 6, the one right next to it, please. Same thing. Once again, I'm gonna distribute that negative. It's the habit that I have. So I've got the 12 plus the 6i. Then a negative times the -5 is plus 5, and a negative times the 13i is -13i. And now I'm ready to collect the like terms. The real parts, the 12 plus the 5 is 17. That's my real part of the answer. Then the imaginary part, 6i minus 13i, or 6i plus a -13i is -7i. Any questions, comments, or concerns about adding or subtracting complex numbers? All right, exercise 7 combines both, so just go ahead and have fun with it. The I term? Yeah, that, so the question, in case you didn't hear it, is do I always put the I term at the end? It is the standard notation to do that. In all honesty, if you wrote that -7i plus 17, that's not something I would mark wrong, but it's just not, like going forward, it's not what you want to do. So remember, order of operations with regular numbers is when you have adding and subtracting, adding is not more important than subtracting and vice versa. You just always go from left to right. So I'm just going to go left to right on this problem. So when I do that, the first thing I hit is this subtraction. So I'm going to take care of that. I got -4 plus 3i, then a -6, and then a plus 7i when I distribute. I'm just going to take this one at a time on this particular problem, but yes, you can do this all in one step. I'm sure most all of you are capable of doing that and probably did. So the real parts now of these first two numbers, -4 and -6 is -10. The imaginary part, 3i and 7i, is 10i. And then I'm going to now combine that with the -6 plus 8i. So now the real part, -10 plus -6 is -16. 10i plus 8i is 18i. And that is our final answer there. So that's adding and subtracting. That's as much as I've got to say about that, because it's just collecting like terms. It's probably knowledge you came in with. Similarly for multiplying. Again, if before class even started, if you did not know I was the imaginary unit, and I said, let's multiply these two things, what acronym would your brain have immediately thought of? Foiling, yes. So we're going to FOIL this. So how do I know to FOIL, Perkster? Well, because there's no sign between the two, okay? When there's no sign, that means to multiply. So I'm going to do my firsts, my outers, my inners, my lasts. So my firsts, 4 times 6 is 24. My outers, the 4 times the 2i. What do you think 4 times 2i is going to give me? Yes, exactly right. 8i. Perfect. My inners, my 3i times 6. What's that going to give me? Yes, 18i. And then last but not least, my 3i times my 2i. What's 3i times 2i going to be? Yes, 6i squared. That's important. Now, just a little hint or tip. I am scatterbrained. I forget this stuff. So before I go and collect my like terms, here's what I would encourage you to do right here. This 6i squared, what is 6i squared equal to? -6. So I would convert that to a -6 right now so that I don't forget to do it, or I don't accidentally add that to the other I terms. Okay, because remember, it's not a like term with the i's because that's an I squared. So that I squared term becomes a real part. So here goes. I've got 24 and -6 for my real parts. That's 18. And then 8i and 18i is 26i. And there it is. First outers, inners last. So you've been doing that since middle school in your algebra classes. All right, exercise 8. 5 minus 4i times 7 plus 2i. I'm going to get started, check my work with your work. So my firsts, the 5 times the 7 is 35. My outers, the 5 times the 2i is 10i. The inners, the -4i times 7 is -28i. And then the last -4i times 2i is -8i squared. Hey, Perkster, could I have those same 4 terms, but in a different order? Yes, certainly. Okay, foiling is just a suggestion. It doesn't matter what order you multiply the terms in. You just got to multiply all 4 pairs together. That's it. Again, before I go on, the -8i squared, what is that term going to become? Yeah, it's going to become +8. Fantastic. So now I'm ready for my final answer right here. 35 plus 8 is 43. And then 10 minus 28 is -18i. Are we good? Is everyone seeing how this -8i squared is becoming the +8? Is that losing anybody? All right, one more multiplying. Then we'll talk about our last of the 4 basic operations. When I go ahead and multiply my firsts together, the 7 times the 7 is 49. My outers, the 7 times -5i is -35i. My inners, the 5i times 7 is +35i. And then my lasts, 5i times -5i is -25i squared. The -25i squared becomes what? +25. And the reason I gave this example is the following. My real parts, the 49 plus the 25, I think that's 74 if I'm adding while I'm talking and doing it right. That's always debatable. But notice what happens to the imaginary parts on this one. They cancel out. I got a negative 35i plus 35i. The reason that happens is because up at the very beginning of this problem, I've got the same two complex numbers with one minor difference. The sign in the middle is different. These get a mathematical term. I'm not, again, super concerned that you remember this word or not, but it's going to apply to our immediate future in about 30 seconds. When you have the same two complex numbers, but the imaginary part has a different sign, these two things are called conjugates. And the reason they merit this special name is because they have this structure that when you multiply them together, you have no more imaginary part. And the reason that that's going to be important for your immediate future is when we divide two complex numbers. Now, if you were in my intermediate algebra class, I talk about division, but not all of the Polk State professors do division in intermediate algebra. So when you divide two complex numbers, like I'm going to do in example 7, there's actually really no division involved. What I want to do, what division means, is I want to get rid of the imaginary number in the bottom. I do not want an I in the denominator, okay? Math people don't like that for whatever reason. I don't know why. So what we do when we divide is we are going to multiply the whole thing by the conjugate. Oh, of the denominator. Let me be clear. The conjugate is just what you get when you change the sign on the imaginary part, not the real part. You don't touch the real part. It's only the sign in front of the I. So looking at example 7, my denominator is 3 plus 2i. So what's the conjugate of 3 plus 2i, would you say? Excellent. 3 minus 2i. So I'm going to multiply the denominator by 3 minus 2i, and I'm going to multiply the numerator by 3 minus 2i. And that's what dividing two complex numbers is. It is simply multiplying the top and the bottom by the conjugate. So it's busy work. Okay? But the nice thing is it's busy work that we pretty much know how to do. It's foiling. So I'm going to go through this. If I get a term that you do not see where I got it, please stop me. Talk to me. Let's hear it. I'm going to start with the numerator. My firsts in the numerator, the 7 times the 3 is 21. My outers in the numerator, the 7 times negative 2i is negative 14i. My inners in the numerator are negative I times 3 or negative 3i. And then the lasts in the numerator, negative I times negative 2i is plus 2i squared. In the denominator, my first, 3 times 3 is 9. My outers, 3 times negative 2i, negative 6i. My inners, 2i times 3 is plus 6i. And then finally, my last 2i times negative 2i is negative 4i squared. Now, I'm not meaning to make a huge mess of this, so I'm just going to do this in pencil so that I don't create more confusion than I need to. Again, before I go and collect my like terms, I'm going to take care of these I squareds. So in the top, the 2i squared, what is that going to be equal to? Negative 2. And then in the bottom, the negative 4i squared, that is going to be equal to positive 4. Great. Now I'm ready to collect like terms, and after I collect like terms, there'll be one more step for you to get to the answer. You've done the hard work though. So in the numerator, 21 minus 2 is 19. The negative 14i minus 3i is negative 17i. In the denominator, if you used the conjugate, the i's cancel, so that's good, and I have 9 plus 4 is 13. If you got there, you have done fantastic work. You've just got one more quick little step. I want to write my answer as a complex number. And so what that means is I'm going to take that 13 in the denominator and I'm going to distribute it. So my first fraction, the real parts to the complex number, is going to be 19 over 13. And then the imaginary part to the complex number is going to be negative 17 over 13. And I like to write the I on the side, but if you're going to write it somewhere, write it with the 17. Okay, if you want to write it as part of the fraction, it goes with the top. Okay, I like to write it out at this as the side because it's a complex number, but that's my habit. It doesn't have to be yours. If you write the I with the 13 in the bottom, that's wrong because our whole purpose was getting rid of the I in the denominator. All right, so make your best attempt. Exercise 10, you're multiplying by the conjugate of the denominator so that you can divide those two numbers. Just to nudge, what is the conjugate you're multiplying by? 4 minus I, great. So keep going. Just want to make sure we're all doing the same thing. 4 minus I. I'm going to get started with the busy work. If you're not done, that is totally cool and fine. Keep working. Check your terms with my terms. If we have something different, please let me know. Starting with the top, firsts, 5 times 4 is 20. My outers, 5 times negative I is negative 5I. My inners, negative 2I times 4 is negative 8I. And then my lasts, negative 2I times negative I is plus 2I squared. In the denominator, my firsts, 4 times 4 is 16. My outers, 4 times negative I is negative 4I. The inners are the opposite of that, plus 4I. And my lasts, I times negative I squared. Then hopefully what you said is, oh, I see those I squareds. They're exciting. The 2I squared right here becomes negative 2. And then the negative I squared becomes a plus 1. And finishing this up, in the top, the 20 minus 2 is 18. The negative 5I and negative 8I is negative 13I. The denominator, 16 plus 1 is 17. And the I parts cancel. That's great news. And then that is a great answer, but it's not fully done. Make sure you write your answer as a complex number. So the real part is 18 over 17. The complex part is 13 over 17 with the I on the side. And there we go. There's one more little thing to talk about with complex numbers. We've added, we subtracted, we multiplied, we've divided, and dividing is just multiplying twice. And so now the last thing is, what happens if I have powers of I that are bigger than 2? We've talked about I squared, but that is defined to be negative 1. But then what happens beyond that? So let me just write this down. Let's say, so we know that I is defined to, that's the definition, that's the imaginary unit. Then we know that I squared, that's defined to be negative 1. So we've got 2 powers of I. We've got I to the first power is just I to the second power is negative 1. So then the question is, what happens with I to the third power? I didn't leave myself a great amount of room here, and I apologize. I need to revise this sheet. So I'm just going to put a blank sheet here so that I have enough room to show you this. So we've got, where am I? There's my hand right there. So I've got I. So I just wrote down, I've got I squared is equal to -1. And now what I want to know is what is I to the third power? So what we're going to do, what I'm going to do is I'm going to break I to the third power down into things that I already know. You remember the way exponents work when you multiply things, what do you do with their exponents? Anybody remember? You add them, yes. So I'm going to break I to the third down into I to the second times I to the first, because 2 plus 1 is 3. And the reason I use those things is that's all I know. So then what is I to the second? What is that defined to be? -1 times I. And so what we get is I to the third power is equal to -I. Okay, that's interesting. Well, let's keep going. I to the fourth power. Again, I'm going to break I to the fourth power down into things I already know. So I'm going to use that I squared because I'm fond of it. So I squared times I squared, 2 plus 2 gives me 4. And each of those I squareds is what? -1. And -1 times -1 is 1. So here's what's going on. I've got I to the first power, that's definition. I to the second is -1, that's definition. Using those two bits, we've created I to the third is -I, and then I to the fourth is 1. Now this is interesting. If I to the fourth is equal to 1, that means in any further power I have, every time I have 4 i's, okay, that is 1. Just cancels out. So for instance, I'm just going to do a couple more because I want to show you the pattern. So let's say if I did I to the fifth, if we keep just kind of going down the chain. Well, I to the fifth, every 4 i's, every I to the fourth, every group of 4 is just going to be 1. So I to the fifth is I to the fourth times I. And then you might be thinking, again, why did you pick I to the fourth? Well, what is I to the fourth? What is that equal to? That's equal to 1. It cancels out. And so what are we left with when the I to the fourth cancels out? Just I. Oh, look at that. It repeats. It goes back up to the top. Well, let's see if that keeps happening. Okay, and then I will share with you the general pattern. If we had all day, we could do this way more and you'd be so excited about it. But I to the sixth. I to the sixth, again, is going to be I to the fourth because there's 4 of them. Every 4 i's I can pick out is just going to be 1. And then how many does that leave over? 2. Thank you. I can't speak, but you knew what I meant. I appreciate it. How many are left over? Well, that's 2 because 4 plus 2 is 6. Well, again, I to the fourth. I to the fourth is equal to 1. So this equals I squared, which, oh, that's right up here, which is -1. And so what happens is the powers of I, if you're interested in the math term, the powers of I create what's called a modular system. Super fun. Math is cool. Anyway, that's just me getting excited. All you have to know is that the powers of I just keep repeating every circuit of 4. So we just saw that I is the same thing as I to the fifth. I squared is the same thing as I to the sixth. So then what would you think I to the third is going to be the same thing as? I to the seventh, and then I to the fourth is going to be the same thing as I to the eighth. And now it's as fun as it is to keep writing powers of I down like this, 9th and 10th. We do long for a quicker way to do this, and there is a quicker way. And the quicker way is this. When you have a power of I, like if I say, let's do the next problem on our sheet. The next problem on our sheet is we're going to simplify I to the 37th power. Now, I do not expect you, although you could if you wanted to, you could just keep listing out the powers of I until you got 37 and see which one it's equal to. But there's a much easier way. Here's what we're going to do. We're going to take the power, the 37, and we're going to divide it into groups of 4. Because remember, every I to the fourth is just 1. Okay, so this is just seeing how many I to the fourths, how many 4-packs do I have of these i's. So 4 goes into 37 9 times and leaves a remainder of 1. I'm not going to list it all out, but what that means, because I want you to understand what's going on and not just mimic what I'm doing. What that means is I to the 37th would be I to the 4th 9 times. I don't really have the patience to write it all 9 times. So I to the 37th is I to the 4th 9 times, and then the remainder is 1, so I have an I to the 1st power on the end. And so what that means for us, again, I want to make this as short and complete as possible, is all that matters is the remainder. The remainder tells me what the equivalence is. So I to the 37th is the same thing because all of these I to the 4ths just cancel out. I to the 37th is just equal to I to the 1st power. And if you listed it all out, that's what you would find out. So maybe you tuned me out because you're not as excited as I am about math. Here's the shortcut. Just divide by 4 and use the remainder. That's it. So I would like you to do that, please. For example 8, simplify I to the 21st power. So I to the 21st power, I'm going to take the 21, I'm going to divide it into groups of 4. And 4 goes into 21 5 times. 5 times 4 is 20, leaves me a remainder of 1. So I've basically given you the same problem I just did. I to the 21st is equal to I to what power? The 1st, the remainder down here, I to the 1st power. Do exercise 12, simplify I to the 82nd power. So we take the 82, oops, I wrote down 81. We take the 82, we divide it by 4. 4 goes into 8 twice. Bring down the 2. 4 does not go into 2, so that's a 0. And that leaves me a remainder of 2 right there. So that means I to the 80, the 2nd power is equal to I to the 2nd. And then I to the 2nd becomes -1. So all that matters is the final power, and everything is going to boil down to either I to the 2nd is -1, I to the 3rd is -I, and then off to the side, I to the 4th is equal to 1. Those are the only powers of I. You'll never see a power of I different than that because everything simplifies down to one of those 4 things.